Hello everyone. My name is Harsh Rajput, and I would like to thank all of you for joining this webinar on critical asset temperature monitoring using fiber optic sensors. So today we will be talking about a very critical area in industrial reliability and safety, that is temperature monitoring of critical assets, and more specifically, how fiber optic sensors are making a big difference in the way we monitor temperature today. From minimizing downtime to preventing equipment failure, fiber optic sensors offer accuracy, reliability, and safety in extreme environments. So we will go through how they work, real-world applications, and how they can be integrated in your asset monitoring strategy. Let me quickly walk you through what we will be covering today. Before we jump in, I will start with a quick introduction to Tempsens instruments, who we are, what we do, and how we are working with advanced sensing technologies. Then we will get into the basics of fiber optic temperature sensing. We will look at how it works, why it's different from traditional sensors. And after that, we will go through a bunch of real world applications. We will talk about how fiber optic sensors are being used in transformers, power cables, and switchgears in the energy sector, conveyor belts and pipelines in the industrial setups, bridges and buildings for structural monitoring, and even in medical equipment for safe and precise temperature tracking. We will also touch on some emerging areas where this technology is starting to make a big impact. Finally, we will wrap things up with a Q&A where I will be happy to answer your questions or hear your thoughts. Let's get started. So Tempsens, established in 1976 as a part of the Pyrotech Group. It is headquartered in Udaipur, Rajasthan, India. It is one of India's leading manufacturers of temperature sensing, calibration, and heating technologies. It has a strong global footprint with subsidiaries in Germany, the USA, Indonesia, Korea, Poland, and Gulf countries. We are backed by ISO certified manufacturing units and NABL accredited calibration labs, ensuring international quality standards. Our vision and mission is simple: to lead the thermal and cable industry with passion, innovation, excellence, and reliability. We bring extensive expertise across mechanical, electronics, and thermal domains. Our team comprises of over 55 dedicated researchers and design engineers. With 13 patents filed and more than 20 industry recognized certifications, we are committed to driving innovation and delivering high quality solutions. So with a wide range of products like contact temperature sensors, including thermocouple, RTDs, gauges, fiber optic sensors, thermal profiling systems, cables, industrial heaters, non-contact temperature sensors like pyrometer, thermal imagers, and furnace monitoring cameras, conductors, furnaces, temperature calibrators. We serve key industries such as steel, cement, power, oil and gas, glass, pharma, and aerospace. Our solutions are designed for reliability and accuracy, even in the most extreme environments. And one of our key innovation in recent years has been the development of fiber optic temperature sensors, especially for applications where traditional sensors fall short, like high voltage zones, electromagnetic interference areas, or extreme heat. Let me walk you through three of our key fiber optic products that are widely used in critical temperature monitoring applications. These are fiber optic distributed temperature sensing, fiber Bragg grating based sensing, and fluorescence-based fiber optic temperature sensing. And each of these products is built with reliability, accuracy, and safety in mind, tailored to different industries and environments. Whether it's monitoring transformers, pipelines, or patient safety in an MRI room, our fiber optic solution are designed to meet your most critical needs. So starting with our first solution, that is fluorescence. It is based on fluorescence material time decay principle. So this system represents a single point contact temperature measurement technique. So it can measure a single point with a single sensor. And at the core of the sensor, there is a fluorescent material which is embedded at the tip of an optical fiber. And the other end of the fiber is connected to a light source, which is used to excite the fluorescent material. When excited, the material naturally seeks to return to its ground state. And in doing so, it emits a photon or a particle of light, we can say. This process is known as fluorescence. And the key to temperature measurement lies in the decay time. That is the time it takes for the material to return to its ground state after excitation. And this decay time varies with temperature, making it a reliable and accurate method for sensing thermal conditions at a specific point. So this is the general specification of the product that Tempsens is making. It has a temperature measurement range of varies from -20 degrees centigrade to 200 degrees centigrade, with an accuracy of ±1 degree centigrade and a resolution of 0.1 degree centigrade. The temperature of each channel can be seen on the display provided on the controller itself, which is a 7-segment digital display. The maximum number of supported channel is 16, and the response time of each channel is 1 second per channel. The communication port for digital communication is RS485 and Ethernet that works over the Modbus protocol. And there is an analog output 420 milliampere industrial standard, which is one for each channel. There are 8 relay outputs so that you can control up to 8 alarms or 8 different systems. Then there is a data logging capability with provided a 1 GB industrial SD card, and it runs on a power supply of 220 volt AC, 50-60 Hz frequency, and it consumes power less than 10 watts. The maximum fiber optic length that the controller support is range from 1 meter to 25 meter, and the operating temperature of the controller is -20 degrees centigrade to 65 degrees centigrade. So the major advantages of fluorescence-based system is it is highly stable with great degree of accuracy, and it is calibration free. So it only needs to be calibrated once, and then it can be used for the application. It is immune to EMI and microwaves. The readings are accurate and reliable temperature readings where thermocouple and RTDs cannot be used. So where thermocouple and RTDs fail, we can use fluorescence-based systems. It has a long service life up to 10 years, and it is maintenance free. The probe size, the fiber sensor size is very small and can be used to measure the hotspot in depth, and it provides real-time readings. So moving on to our second solution, that is Dtsenz, which is based on fiber brick grating technique. So fiber brick grating is a new and a non-conventional sensing technology used in wide variety of applications nowadays. It is designed in sensing applications where there is electromagnetic and RF interference. It is light in weight, compact, and intrinsically safe to use in hazardous environments. So this is a basic overview of the fiber brick grating sensors. So unlike fully distributed sensing systems, which measure temperature or strain continuously along the entire fiber length, FBGs are quasi-distributed. This means we place multiple FBGs at specific points along the fiber, each with a unique Bragg wavelength. Then by sending the light through the fiber and analyzing the reflected wavelength, we can monitor temperature or strain at each FBG location independently. So basically, we put different FBGs on a single fiber at a predefined location. Okay, so a fiber brick grating is a specialized structure created within the core of a single mode optical fiber, which is formed by exposing the core to an intense ultraviolet light. And these planes act like a partial mirror, reflecting a specific wavelength of light while allowing other to pass through. And this reflected wavelength is called the Bragg wavelength, and it is the key to the sensor's functionality. So this is the major part of the FBG based system, the Bragg wavelength, which gets reflected from the gratings. And when the fiber is subjected to strain, like stretching or compressing, or temperature changes, which also causes a stretch or a compress in the fiber core, the grating period and the refractive index both changes, and this results a shift in the Bragg wavelength. So by measuring the wavelength shift in the reflected light, we can accurately determine the amount of strain or temperature change affecting the fiber. Currently, we are working on the temperature sensing, and we will further move to strain and other physical parameters also. So these are the specification of our Dtsenz system. The maximum number of supported channels is 16. So you can connect 16 number of sensors, and each sensor can have 20 sensing points maximum. So 16 into 20, you can have a 320 sensing points. The response time ranges from 1 milliseconds to up to seconds or minutes. And maximum number of FBGs per channel is 20. Then the temperature range it can measure varies from -40 degree to 900 degree centigrade, which is a very good temperature range. A specialized fiber are used for measuring temperatures in 900-degree ambient. The temperature resolution is 0.1 degree and the accuracy is maintained at plus minus 1 degree centigrade. The sensor cable length can be 5 kilometer lead-in cable and 5 kilometer sensor cable. So you can have 20 number of points anywhere on that 5 kilometer sensor cable. The fiber type used in this technology is single mode fiber with a 9 micron core and 125 micron cladding, which is a standard fiber. And the operating temperature of the controller ranges from minus 20 to 65 degrees centigrade. It also operates on 220 volt AC, 50-60 hertz, and the voltage converter is provided by us. The communication interface available are USB, RJ45, and RS485. So the advantages of Bragg system. The major advantage is its multiplexing capability. Like you can daisy chain multiple type of sensors to a single interrogator, and you can measure multiple physical parameters using a single cable. Like if you want to measure temperature, you want to measure pressure, you want to measure strain, you can do with a single interrogator, and you just have to daisy chain the sensors. There is low loss relative to the fiber length, immunity to electromagnetic and radio frequency interference. The sensors can be very small in size and weight, and they are very safe to operate in hazardous environment. They are inert to most of the chemicals, and they have a very high sensitivity to the physical parameters, and they have a long-term reliability. Moving on to our third solution, that is Dtsenz, distributed temperature monitoring system. Let me introduce to you distributed temperature sensing, or DTS. So it is a linear heat detection system that doesn't rely on multiple traditional sensors. Instead, it uses a single strand of fiber optic cable to continuously measure temperature along its entire length, detecting changes at every meter. So using a single fiber optic cable, you can measure temperature up to kilometers. So what remarkable is that the fiber itself is the sensor. You don't have to do any, you have to make any gratings, or you have to add any additional sensor to it. Simple fibers can be used as a sensor. Then the second point is there is no need to install dozens or hundreds of individual sensing points. So this technology is especially used for applications like fire detection and long distance temperature monitoring. Think tunnels, pipelines, conveyors, or industrial plants. And DTS system can monitor temperature over several kilometers, offering a detailed temperature profile of the entire area in real time. So it's an efficient and scalable solution for anyone needing reliable, continuous thermal monitoring across large areas. So Dtsenz is basically designed for larger areas, and it is not feasible for shorter areas or small areas. So the basic working principle of DTS. So in a DTS system, a short pulse of laser light is transmitted through the optical fiber. As this light travels, a small portion of it is scattered back toward the source due to natural interaction with the fiber. And this is known as backscattering. Then there are two types of scattering that are of interest here. Relay scattering, which relates to fiber integrity, and Raman scattering, which provides thermal information. So Raman scattering produces two components: the Stokes signal, which has lower energy, and the anti-Stokes signal, which has higher energy and is highly sensitive to temperature. And by analyzing the ratio between these two Raman signals, we can accurately determine the temperature at each point along the fiber. Now, how do we know where the temperature change is there? So how do we know where along the fiber the temperature change is occurring? So this is done using the method called optical time domain reflectometry, or OTDR. So when the laser pulse is sent into the fiber, we measure how long it takes for the backscattered light to return to the source. And since the speed of light in the fiber is known, this time delay tells us the exact position along the fiber where the scattering is happening, and therefore the temperature measurement took place. This combination of Raman scattering and OTDR enables continuous temperature profiling along kilometers of optical fiber, providing real-time distributed thermal monitoring with pinpoint accuracy. Now, this is the specification for the Dtsenz system. There can be up to 20 number of channels, so you can connect 20 sensor fibers on a single controller. The sensing line can be up to 20 km per channel. So 20 into 20, you can measure 400 km. The fiber connectors are FC APC type. The special resolution. Special resolution is defined as like the amount of fiber to be heated to get the accurate reading. So it ranges from 0.5 meter to 2 meter. Then the location accuracy is 0.5 meter. Temperature accuracy is plus minus 2 degrees centigrade with a resolution of 0.1 degree centigrade. The sensing range, which is dependent upon the fiber itself, varies from minus 40 to 200 degrees centigrade. And the response time is 5 seconds per channel. The outputs provided are RS485, which works on Modbus protocol, RJ45, which have UDP TCP IP protocol. And it works on the power source, 220 volt AC, 5060 Hz frequency. These are the two standard types of cables that are compatible with the Dtsenz that we suggest. So the primary difference between them lie in their construction and operating temperature ranges. So the first cable shown on the left is designed for fire detection application. It is suitable for low temperature environments with an operating range up to 120 degrees centigrade for short-term exposure and up to 85 degrees centigrade for continuous use. And the second cable, it is a heat resistant sensor cable engineered for high temperature environment. So it can withstand temperatures of up to 200 degrees centigrade for short-term exposure and up to 150 degrees centigrade for continuous operation. Each cable type is tailored for specific use cases, ensuring reliable performance and accurate temperature sensing across various industrial and safety critical applications. This is the software screen. So distributed temperature systems are designed to deliver high resolution, real-time thermal monitoring over extended length of optical fiber. So one of the core functionalities of DTS system is real-time data acquisition, wherein temperature measurements are continuously recorded along the entire length of the fiber. These readings are processed and stored in a dynamic database, enabling operators to access time-stamped thermal data for immediate analysis. So the data for the whole cable is recorded in real time, and thus it enables the operators to access them. The system architecture supports customizable zone configuration, so allowing the fiber to be segmented into discrete monitoring zones. So we can divide the fiber into multiple zones depending upon the area where it is installed. So these zones can be defined based on the application specific requirements, such as critical infrastructure points. We can divide it into environmental segments, or we can divide as per the asset location. Different assets, we can divide as per the different assets with user-defined temperature thresholds. So each zone can have their own temperature threshold. Some can have the alarm at 100 degrees centigrade, some zone can have at 80 degree, and like that. So this zoning capability provides granular control over alert generation and enhances that system's ability to localize and respond to thermal anomalies. Additionally, DTS system generates a linear temperature profile with spatial resolution as fine as 1 meter or 0.5 meter. So this means that the temperature data is available for every meter of fiber, providing a detailed and continuous thermal map of the monitored asset or environment. So the resulting thermal profile allows for precise identification of hotspot, thermal gradients, and unusual patterns. So by using this thermal profile, which are critical for early fault detection, insulation integrity assessment, and system reliability analysis. Together, these capabilities make DTS an invaluable tool for advanced thermal diagnostics in applications such as high voltage power cables, pipelines, tunnels, and industrial process monitoring, delivering both operational insight and safety assurance. So now moving on to our topic, critical asset temperature monitoring. These were the three products. Now let's see how these products can be used in monitoring of critical asset temperature. Starting with transformer winding hotspot temperature monitoring. So transformer winding temperature is one of the most critical parameters to monitor in power transformers. Why? Because it directly impacts how well the transformer performs, how reliable it is, and how long it lasts. So when the transformer gets too hot, their insulation ages faster, which can lead to early failures. And with the grid becoming more stressed due to higher demand and more assets being pushed to their limits, keeping a close eye on temperature is more important than ever for utilities and transmission and distribution companies. So, but there is a challenge in this. So here's the challenge. Measuring the temperature inside the transformer winding isn't straightforward. These zones are electrically harsh environments with very high voltages and strong electromagnetic interference or EMIs. So traditional sensors like RTDs and thermocouples often tends to fail here because of EMI and lack of electrical isolation. So moreover, calculated temperature values based on external measurements or models are not reliable enough for critical decision. Without precise real-time data, utilities risk transformer overload, accelerated insulation aging, and unexpected outages. What will be the solution? So we suggest a fiber optic solution. This is where fiber optic temperature sensors come in. Unlike conventional sensors, fiber optic sensors are immune to EMI and completely dielectrically safe because they don't have conductive parts. And this allows them to be embedded directly into the winding hotspot. So the fiber optic sensors can be installed directly between the windings, providing a real-time temperature of the windings. The places that get hottest inside the transformers. Okay, so by getting accurate real-time temperature data from these critical points, utilities can safely push transformer closer to their design limits without risking overheating. So this is the major benefit to the transformer companies in increasing the life of the transformer. How the implementation take place? Typically, these fiber optic sensors are installed during the manufacturing process or retrofitted exact placement of fibers based on thermal simulation or industry standards like IEC and IEEE. So there are standards like IEC and IEEE that provides the best location for placing the sensors. The connect to a fluorescence controller unit, which feeds real-time data into the transformer SCADA or monitoring system. With configurable alarms and data logging, this setup supports smarter load management, better thermal modeling, and predictive maintenance. Ultimately, this approach helps utilities to optimize peak loads, detect faults early, extend transformer life, and reduce maintenance cost, all while keeping operations safe. So our next application is switchgear temperature monitoring. So switchgears are essential for controlling, protecting, and isolating electrical equipment. However, the joints, terminations, and busbar inside can develop high resistance over time, so leading to localized heating. And if left unchecked, this hotspot can cause insulation damage or even fires. But the challenge lies in monitoring temperature inside a confined high voltage cabinet where conventional sensors can't operate safely due to the electromagnetic noise and presence of high voltages. So the fiber optic solution is installing a fluorescence-based system or a Dtsenz, that is FBG-based system. And fiber optic sensors, being dielectric and compact, can be installed at critical junctions to provide continuous real-time temperature monitoring. And these sensors don't interfere with the electrical field and are resistant to EMI. By detecting abnormal temperature rise early, operators can take corrective action, reducing unplanned outages and improving operational safety. And fluorescence or Braxton's temperature monitoring system conducts real-time monitoring to accurately measure temperature at switchgear contact points and cable joints, which make ideal maintenance at unmanned substations. Third application is structural health monitoring. So over the time, structures like bridges, tunnels, and dams face wear and tear from environmental factors like load stress and aging materials. Traditional inspection methods are often manual and periodic, meaning problems can go unnoticed between the inspection periods. That's where fiber optic sensors come into play. Especially FBG arrays or distributed sensing using relay scattering can be embedded in concrete, rebar, or affixed to structural surface to monitor parameters such as strain, displacement, and temperature changes. So in this application, Braxtons can be used to detect the temperature, strain, displacement for the structural health monitoring. And this real-time data helps engineers understand how a structure is behaving under stress, detect crack formation early, and assess fatigue over time. So the technology enables predictive maintenance strategies, thereby improving public safety and reducing long-term repair cost. Now our fourth application is oil and gas pipeline leak detection. So in the oil and gas sector, pipeline integrity is mission critical. A small leak can cause environmental disasters, huge financial loss, and even endanger lives. Detecting leaks in vast remote areas is extremely challenging using traditional sensor technologies. Distributed temperature sensing and distributed acoustic sensing using fiber optics can continuously monitor the entire pipeline length for anomalies in temperature or vibration. Currently, we are manufacturing distributed temperature sensing here. So this system detects leaks, intrusion attempts, or third-party interference in real time. So by burying a fiber optic cable alongside the pipeline or attaching it to the outer shell, operators gain a 24/7 surveillance system that pinpoints problems to within a few meters, and it allows for faster response, minimize spill size, and ensures regulatory compliance. Our next application is conveyor belt monitoring. And this is a major application because most of the plants, cement plants, uses conveyor belts. So conveyor belts are extensively used in industries such as mining, cement, cement production, and bulk material handling, where they facilitate the efficient transport of heavy and abrasive materials over long distances. However, a significant risk in this operation is the overheating of the critical belt components, particularly rollers and idlers, which are responsible for support and guiding the belt. And overheating can rise from various factors, including the friction caused by misalignment, bearing wear or failure, inadequate lubrication, or excessive material loads. And if not detected and addressed early, this overheating can escalate, leading to severe belt damage, such as tears or degradation, and extreme cases, sparking fires that pose serious safety hazards and environmental risk. So these incidents can result in unplanned operational shutdowns, costly repairs, and substantial production losses, impacting both profitability and operational efficiency. And to mitigate this risk, industries are increasingly adopting advanced monitoring technologies such as infrared sensors, thermal imaging, and smart idlers equipped with embedded temperature and vibration sensors to enable real-time conditioning monitoring. Routine maintenance practices, including regular alignment checks and lubrication schedules, are critical to preventing overheating and extending the life of the conveyor systems. So the fiber optic solution in this case would be Dtsenz temperature monitoring system, as it is suitable for long conveyor belts and it can measure temperature continuously over the whole profile of the conveyor belts. So using DTS, we can lay fibers along the length of the conveyor structure to detect localized heating. And these sensors provide continuous temperature profiles along thousands of meters. And when a bearing starts to fail, it heats up, and the fiber system immediately flags that zone. Maintenance team can be dispatched before a serious failure occurs, and this predictive capability ensures uninterrupted operation and reduced maintenance costs significantly. Our next application is power cable temperature monitoring. So modern electrical grids rely heavily on underground and submarine XLPE cables. Overloading, aging, and changing soil or seabed conditions can cause thermal buildup, leading to insulation failure. And with fiber optic DTS, installed along or inside the cable sheath, utilities can monitor temperature at every point along the cable in real time. And this data allows for dynamic cable rating DCR, where operational limits are adjusted based on the actual condition instead of conservative estimates based on calculations. So fiber optic technology can be used to improve the safety and efficiency of underground and submarine power cable, medical and biomedical application. So in clinical settings, precise, real-time, and safe temperature monitoring is not just important, it's critical for patient safety and treatment efficacy. Here we are talking about the life of a human. So whether during MRI scans, cancer therapies like hyperthermia or thermal ablation, or the delicate monitoring of neonatal infant, temperature fluctuations can significantly impact outcomes. So traditional temperature sensors such as thermocouple or RTDs often pose challenges. They can be invasive, bulky, or electrically conductive, leading to signal interference with highly sensitive medical imaging equipments like MRI or CT scanners. So, moreover, the use of metal-based sensors in such environment can be dangerous due to presence of strong magnetic fields. That's where fiber optic sensors can be used, like fluorescence or FBG-based system. which offers a non-invasive, non-metallic, and biocompatible alternative. And these sensors are completely immune to electromagnetic interference and electrically passive, making them ideal for use in harsh electromagnetic environments. And they can be safely used inside the human body, integrated in surgical tools, embedded in catheters, or mounted on skin surfaces to continuously monitor patient temperature with high spatial and temporal accuracy. Additionally, additionally their compact form factor allows them to be used in applications where space is extremely limited, such as inside minimally invasive surgical instruments or implantable medical devices. Overall, fiber optic sensors are revolutionizing temperature monitoring in healthcare by offering safer, more accurate, and patient-friendly solutions across a wide range of medical applications. These are some of the other emerging applications other than we have discussed earlier. So EV batteries to monitor the thermal runaway in modules, railways to measure axle temperature or tunnel heat, aerospace we can track turbine and engine zone heat, in nuclear power plants because fiber is safe in high radiation environments, and it can be used with the wind turbines to monitor blade and rotor temperature, lightning damage, etc. These applications highlight the adaptability and robustness of fiber optic sensing in environments where electrical sensors would fail or pose safety risks. Thank you all.